Hello everyone, my name is Hafiz and I'm presenting my project for subject INE 504. The title that I choose is Texturing Techniques on Monocrystalline Silicon to Improve Solar Cell Efficiency. Okay, so these are the three journals selected that I proposed and also approved by Dr. Sampio. So the first one is the comparisons of mechanical and ultrasonic agitation method for monocrystalline silicon texturing, which was published in 2016. And the second journal that I selected is the title is Silicon Wafer Surface Reflectance Investigation by Using Different Surface Texturing Parameter. So this has been published in 2018. And the last journal in the list that I've selected is the direct fabrications of cone arrays microstructure on a monocrystalline silicon surface by femtosecond laser texturing. So this has been published in 2017. And the reference of the authors are listed below here. So the first journal, title of comparisons of mechanical and ultrasonic agitation method for monocrystalline silicon texturing. And yeah, so from the executive summary from this journal, the first is that the journal is using established, well-known process fabricating monosilicon solar cells, which currently industry, which is using alkaline etching process in this study. So it's using a hot temperatures process above 60 degrees solution mixed with DI water, potassium hydroxide or KOH, isopropyl alcohol IPA to form optimized micropyramid shape texture. And here what they introduce is enhanced additions methods or techniques, which is the agitations to existing alkaline process. The objective is to reduce or eliminate the hydrogen bubbles released during the current conventional alkaline etching process, which when the KOH reacts with IPA, they produce these hydrogen bubbles, then later create a oxide on top of the surface of monocrystalline silicon. And there also has been reported other methods to reduce this bubble by increase KOH, but then they will induce the non-uniformity of texturing on top of this surface. Uh, so in this journal, they are comparing two types of agitations. One is mechanical stir agitations, and the second one is using ultrasonic vibration agitations. Let's have a look on the research methodology for this journal, where they start by preparing the p-type monocrystalline CZ silicon around 1 to 3 ohm per cm, and then dip into 1% of hydrofluoric acid, rinse with DI water, and go to the subsequent process, which is the alkaline etching process. Solutions of DI water mixed with KOH and also IPA solutions. And in this journal, they evaluate the core concentrations of 1 to 7, and IPA is 3 to 8 volume percentage, and temperature between 60 degree to 80 degrees C. And in this journal, it's split into two approach or two techniques. So the first one is mechanical agitations, and the second one is ultrasonic agitations. And after complete either mechanical or ultrasonic agitations, they go to rinse with DI water, followed by hot N2 drying and cleaning with HF HCI, RCA2 mix solutions, and followed by rinse with DI water, POCl3 diffusions at 838 degrees C, and again cleaning with HF, HCI, RCA2 cleaning, and proceed with the next process of the CVD anti-reflections, and going towards the metallization and firing, and move to the last process of laser edge isolations. Okay, next slide is talking about the results and the discussion from this journal. So the results of the pyramid shape on the monocrystalline silicon surface coverage has increased with the process time if using options of mechanical agitation. However, with another method which is using ultrasonic agitations, there has been reported 100% of surface coverage without process time independence. So on this picture on the right side here, you can see this is the mechanical agitation under the SEM image, and you can see there is a lot of empty space comparing to ultrasonic agitation, which fully populated by the pyramid shape. But here also we can notice that the texturing size of the pyramid are relatively smaller on the ultrasonic agitations, and it's bigger on the mechanical agitation. But then the intensity or density, the density of the pyramid population is much more on the ultrasonic agitation compared to mechanical agitations. And this directly translates to the numbers of pyramid shapes per mm² on top of this monocrystalline silicon surface. As you can see here, at the both are at the 70 degrees process of alkaline etching, and these are the time horizontal axis. This is number of pyramid per mm². And if you can see, the mechanical agitations are decreasing in terms of numbers of pyramids over the time, but then the ultrasonic is increasing over the time, except for the first results. It's slightly higher compared to the rest. So, but then you can see it is not a time dependence, and it's roughly relatively more compared to mechanical agitations. And based on the results, ultrasonic agitations proven to be more effective methods with optimized parameter resulting in less than 5% reflectance. This can increase the solar cell efficiency, and on top of that also it's better in terms of productivity time compared to mechanical agitation. Okay, on the next journal, title of a silicon wafer surface reflectance investigation by using a different surface texture parameter. In here, what I found as a summary, it's create high aspect ratio of a random ceramic structure texturing on top of monocrystalline silicon, and it's also talking about comparing mechanical grinding and as well as alkaline etching and combinations of both methods. The mechanical grinding abrasions using the aluminum oxide Al2O3 powder to create a roughness on top of the surface of monocrystalline silicon. Different grains size regards to refractive index or reflectance was investigated. Alkaline etching process with different solution concentrations also been evaluated. And the last objective of this journal is to combine both methods and to see whether it's give a better results between these two, or it's almost the same result with either mechanical operations or alkaline. So the way the combinations method work is that start with the mechanical grinding first to create a certain roughness, then later being etched out by the alkaline etching process. Okay, next slide. Let's look at the research methodology for Journal 2, where you start with the material preparations of monocrystalline silicon, size of 1 times 1 cm squared, thickness of 280 micrometer, and it goes to mechanical polish process, split into two. As I mentioned earlier, that in this research or journal, they have been evaluated of three types of different techniques. At first, it's split into two. First is mechanical grinding, and the second one is split into the chemical alkaline etching. The first splitting into mechanical grinding is using a aluminum oxide and also water to create a surface roughness. And in here, there's three different type of grain size of aluminum oxide has been evaluated, from the smallest 8 micrometer up to the biggest 22 micrometer. And here again, it's split into two. So the first is to get the relevant data with the mechanical grinding method, and the second one is continue with the chemical alkaline etching. So over here, number 2, which only with chemical alkaline etching, and number 3 is with the combinations of mechanical grinding as well as the chemical alkaline etching. So in chemical alkaline etching process, it starts with the cleaning with solutions of DI or DI water mixed with NH4OH and also H2O2. And it's proceed to another cleaning, again DI water, but this time is mixed with a different chemical, which is HCl as well as H2O2, and then proceed to the etching process, which solutions of DI water, KOH, and IPA solutions. And over here, there is several of concentrations has been evaluated, three of them. So the first one is with 1 m or 1 mole, 5 mole, and last one is 7 mole concentrations. Fixed temperature at 70 degree C Celsius, and durations of this process also fixed at 15 minutes. And the last process is rinsed with DI water. And here I also put in the legends here, so that self-explanatory. So the first sample is mechanical abrasive samples here. Second one is the alkaline etching samples. It's coming from here. And the third is combined samples coming from here. Right, next slide is results and discussion for Journal 2. Yeah, from this table in figure 2, what I can observe is that the reflectance result comparing of aluminum oxide grain size has a difference significantly, and solutions concentrations of DI, KOH, and IPA also have a significant difference, and both combined also give different results. So the first is talking about the mechanical grinding results. So what I observe is that the grain size of 8 micrometer shows the best results among the other mechanical grinding results in abrasive methods, with the reflectance achieved was about 16.4%, comparing to the bigger size of the aluminum oxide 22 micron reflectance of 23.97%. So the lower reflectance mean better in terms of absorption. So over here, 8 micron is better compared to 22 micron grain size in terms of mechanical grinding method. The second point here, which also referred to figure 2 table, high concentrations at 5 moles of DI, COF, and IPA give worse results of reflectance of 26.3% comparing to low concentrations at 1 mole, which giving the reflectance of 31.6%. This means that the lower concentrations of 1 mole is better compared to 5 moles. And there is no results of 7 moles has been reported, but then inside this table there is a 7 mole combinations of mechanical grinding and also chemical etching. The next observation is the combinations of both world abrasions as well as the alkaline etching give the best uh, solutions or the best results comparing to both techniques, which give the lowest reflectance at 11.85%. And the combination method does prove each complement each other in optimizing a pyramid shape, whereby the best of a grinding results mix with the best in the alkaline chemical etching give the best of two worlds, better than the two worlds. But then this can be further studied with the smaller um, aluminum oxide grain. As of now, in this study, it's only up to 8 micrometer, and also the concentration also lower up to 1 mole, and this can be further evaluate to understand where is the saturated state. Okay, the last journal um, which I selected, the title of direct fabrications of cone array microstructure on the monocrystalline silicon surface by using a femtosecond laser texturing. So unlike the other two journals, this is using a different method uh, from the alkaline chemical etching, whereby this is using direct laser expose or laser ablations on top of the micro mono silicon uh, monocrystalline silicon surface. And this journal is talking about evaluate form of quasi-uniform cone array, or known as a microstructure, by using a femtosecond laser. It targets to produce the homogeneous mesoporous structure on top of mono crystalline silicon surface. Texture or structure created from this laser ablations or laser exposure process was studied. Evaluation was carried out under a normal environment without any other influence, external influence, or any further optics, chemical etching, nor even a vacuum chamber. So in here also they did a study in terms of several parameters that contribute to the laser ablations process, which leads to the key focusing on the uniform texturing on monocrystalline silicon surface, which evaluating the femtosecond laser parameter of focus depth, output power, scanning velocity, and interval. Let's have a look on the research methodology for this journal. So the first prep material using here is the P-type monocrystalline silicon wafers, thickness of 200 micrometer with non-polished wafer. And then it's moved to the ultrasonic DI water cleaning for 15 minutes duration. Proceed to the laser texturing process. And then this laser texturing have built-in, or the equipment itself was come together or built in together with the CCD computer monitoring feedback to the equipment to give or to control the laser texturing or laser ablations. So it gives the feedback controlling in terms of shutter, attenuator, and also XYZ stage or tables. And the next process is cleaning, again with the ultrasonic, the air water, for 5 minutes durations. So this is the end of the process. Although it's a simple kind of methodology flow, but there's a lot more complex sequence inside this laser texturing alone, which being illustrated in this diagram here. I put it in the bottom left. So in this laser texturing equipment itself, the process or the methodology are quite complex. It uses 800 nanometer with 35 frame per second and modulate at 1 kilohertz laser source fired to the beam splitter. One is going to the power meter to control the laser power, and then another one is going directly to mirror, and mirror guiding this laser beam into a shutter as well as a attenuator, and being reflected with another mirror to the interest samples or interest sample surface, which sits on top of XYZ table or stage. And the stage is being controlled or feedback from the computer, as well as the shutter and also attenuator, and it's being monitored by the CCD camera on the so-called over during processing process, and all of this being monitored by computer and being controlled feedback by computer based on the recipe that we created in this equipment. So it's a bit more complex if we look into the laser equipment itself. The results of this journal 3. Um, the results reported that the focus depth gives the significant factor in terms of forming uniform quasi-cone array. The focus depth of 0 micron to 10 micron shows the shapes of perpendicular curve can be observed on the treated area or treated surface of a monocrystalline silicon, as shown in here, figure 3. And yeah, the focus depth of more than 20 micron shows perpendicular groove disappear and the cone-like shape are formed. The quasi-uniform cone array can be obtained with a focus depth of 20 micron and 30 micron. If you can refer to this diagram on the right side, it's comparing the picture, 3D picture of 0 micron of focus depth until up to 40 micron focus depth. And the groove start to disappear. The groove of the perpendicular, you can see here, these are the group of the perpendicular area, start to disappear when the focus depth reach 20 micron and above. However, up to 30 micron, only that the cone shape spike are formed. And if you look at the 40 micron focus depth, there's no longer cone shape can be observed. Therefore, in this parameter, we can make use of 20 micron and also 30 micron to understand which are the most optimized parameter in terms of focus depth. And minor surface defects on monocrystalline silicon created by the initial laser path can also cause a non-uniform depth. And solution to overcome this issue is to have a better control of radiation laser energy, density, melting time, and also ripple pattern. And these are the complex parameter and very sensitive to control. Next point is optimize focus depth. Based on this study, has shown that a 20 micron focus depth creates 8 micron cone spike height, and which resulting the best in terms of lower reflectance at 9%. The next slide is talking about the overall conclusions comparing of the journal 1, journal 2, and journal 3. So for journal 1, what I can conclude is that it less complex and it is enhancement into a current established chip process and well-known process that being mass production currently in the making of a solar panel. And yet the introduce of method are ready to implement for mass production, and it is improved significantly in terms of results among other methods in other journals. And journal 2, what I can conclude is that it's introduced a new kind of a preparation process whereby the wafer is being exposed to abrasive surface or roughness surface with powder from aluminum oxide to create certain roughness, and then continue with the common known alkaline etching process. However, this study is only limited to a small grain size of 8 micron, and it does not cover the many interactions of in terms of saturated state of the grain as well as saturated state of the concentrations in the alkaline etching solution. However, this can be further studied from what has been reported now in Journal 2. In Journal 3, the conclusion that I can make is that it's used a direct process, which means that exposed to laser ablations and create a microstructure of cone area. However, this lasing process, ablation lasing process, is sensitive and complex parameter need to be thoroughly controlled in order to create or to form a uniform kind of cone uniform cone area microstructure. So it is also only applicable for thick monocrystalline silicon. The reason is because to avoid melting during the process. And when it comes to a thick monocrystalline silicon, this also will impact the cost of a material, and laser equipment also is not cheap and expensive equipment compared to the chemical etching. As a summary, yeah, I choose the first journal, which is comparisons of chemical and ultrasonic agitation method for monocrystalline silicon texturing. It is because of alkaline etching is commonly used to fabricate solar cell, and agitation is also not new process in fabrications or in the mass productions. And combining these two established process make it perfect solutions and easy to adapt and introduce. Therefore, it less interaction risk because of agitation is using external process instead of influencing direct concentration solutions reactions. And the way that this journal address is understanding of the current state, process weakness or process issue or problem, and try to eliminate or reduce those problems and make use of the existing established, improve, optimized process. And the proposed solutions are simple process and it's simple to integrate for mass productions. Out of all method in 3 journals that I've compared, these are the best in terms of reflectance results, which is reported less than 5% comparing to other methods. Alright, that's all about it for me, for my project presentation. Hope you enjoy and thank you. Have a nice day.